Chapter 6, Hunt for the Tin Man's Heart. And this here is a quote by Robert M. Persig from Zen and the Art of Motorcycle Maintenance. Phaedrus was a master with his knife. With a single stroke of analytic thought, he split the whole world into parts of his own choosing, split the parts and split the fragments of the parts, finer and finer, until he had reduced it to what he wanted it to be. I look for reality and try to tell you what I see there. The words and pictures come out of the past. My mind goes back as I drive past the creek where, as a child of 5 or 6, I was the expendable test pilot to try a raft the older children had made from scrap lumber and empty oil cans. I drive over that culvert built at the edge of town in the 20s, past a part of my life in half a second, a place that was once a whole world surrounded by thick briars and stubby green trees with gravel beneath the spring waters where crayfish and red, white, and blue minnows darted and hid. There was a world of mystery and wonder down that square concrete corridor beneath the street for those who dared. In that half second, I feel like many people remembering other lives, strolling down corridors, looking through doorways into other worlds than my world here and now. And I hear a voice from the past calling my name. Bookie, come on in now. My mother, who died a decade ago, says to me, come on in, it's time for your supper. I turn again, and I am back here with you, searching for reality, searching and thinking about the things that physics has found and what they mean, what they tell us about what reality is. The Heisenberg and Schrödinger equations have led us to a wondrous understanding of reality, far more penetrating than had been revealed by classical physics. It is safe to say now that nothing that we see in this world lies outside the breadth and scope of quantum mechanics. With this analytical tool, we can examine the detailed workings of the atoms, determining how they are put together, how they radiate light, and how they combine into molecules. We can put these atoms and molecules together so that they make the materials of our world, and in doing this, understand what makes their strength and their color. Know why metals feel cool, why the stars shine, and why glass is brittle, the ocean's wet, and the sky blue. We use this knowledge of quantum mechanics to make computer parts that automate our work, to create lasers and optical fibers that carry calls from door to door, and to develop all the wonderful superconductor technology. Quantum mechanics explains all these things and all the things classical physics had explained before. Quantum mechanics is being used to design new drugs to heal and medicate our bodies. It is being used to understand the delicate machinery of life, of reproduction, of evolution. Its offspring fills our newspapers with tales of nuclear power, worries of nuclear war, designs for weapons for future wars, and defenses for future peace. Its products, such as magnetic resonance imaging, MRI, and positron emission tomography, PET scans, let us peek into the structural and chemical makeup of the living tissues of the body, and with the aid of the scanning tunnel microscope, STM, we can see individual atoms. The consequences of quantum mechanics, the fruits, the benefits, and the liabilities, permeate our lives. The results are all around us, because quantum mechanics not only describes the atomic world, but also embraces the equations of classical physics, Newton's equations. It describes everything in our world. It seems it has all the answers. We only enumerate the basic pieces of matter, write down the forces acting on them, and turn the crank. Out will come the answer to every question about the nature of our reality. All we have to do now is find out what the basic pieces of matter are, and the equations of quantum mechanics will describe all the patterns in nature. That is the way it looks, and that is the strategy of modern physics. This next section is called Violets by the Yellow Brick Road. Quantum mechanics works in a strange way. The way it should work is not the way it does work. It is not set up to describe how things actually are, but to work in terms of the way we think about these things. To solve the problem of the hydrogen atom, we pretend that the hydrogen atom really looks the way Bohr described it. We say that we have a nucleus consisting of a single positively charged proton and a point-like negatively charged electron at some position near the proton moving in some direction that is specified by a set of coordinates. We add to this an expression representing the force acting between the charges on the proton and the electron, actually a term that represents the potential energy in the electric field that surrounds the proton. And then we say that this result tells us the energy of the whole thing as though we were describing the motion of a planet moving around the sun. When this very classical picture of the parts and pieces of the atom is complete, we make some prescription-like replacements. The momentum is replaced by a term that spells out how that probability amplitude changes. Its rates of change as we move from place to place. The potential energy term representing the forces has to be multiplied by that probability wave height, and the energy is replaced by a quantity that says how rapidly the wave varies in time. Then we turn a big mathematical crank, and this strangely distorted classical picture begins to spit out a series of quantum pictures of the hydrogen atom. Each picture has its own pattern that describes not where the electron is, but where it might be. The simplest of these arrangements is just a spherically symmetric puffball, a dandelion pappus of a pattern. Other patterns look like very symmetric flowers with petals that reach out in every direction. There is a whole series of these electron probability patterns. With each successive picture in this series of probability patterns, the electron is extended into more and more probability petals that reach farther away from its nucleus so that the atom has a higher energy. When an atom is in one of these higher energy levels, we say that it is in an excited state. That, then, is how quantum mechanics describes the hydrogen atom, and the description of all other atoms turns out to follow nearly the same procedure, but with a rather peculiar and quite significant exception known as the Pauli exclusion principle. This principle, named for Wolfgang Pauli, turns out to have a very basic role in determining the way the world works and looks. It causes the atoms of different elements to take on the various flower-like forms that the Schrödinger equation describes as possibilities, rather than all the atoms looking the same, as would otherwise be the case. In the hydrogen atom, in its ground state, the way it ordinarily exists, the one electron sits in the lowest energy shell, a spherical blob of uncertainty surrounding the atom's nucleus. In helium, the next element up Mendeleev's atomic ladder, there are two positively charged protons in its nucleus, along with two uncharged particles, called neutrons, and two negatively charged electrons surrounding the nucleus. Although there is a repulsive force between the two electrons because of their electric charge, they still both squat down into the same ground state configuration of a ball-like fuzziness around the helium nucleus. Because this nucleus with its two protons has more positive charge on it than the hydrogen atom with its single proton, that fuzzy helium ball of electronic uncertainty is even more tightly held and smaller than the hydrogen atom. Lithium has three protons in the nucleus tugging on three electrons. Something new goes on there. The first two electrons are in an even tighter hydrogen-like fuzzy ball around the nucleus, but the third electron cannot drop down near to the nucleus with the first two. The first two electrons are in the lowest atomic shell, but the third electron occupies an electronic shell outside of these. It occupies a fuzzy double-lobed blob of an orbit. With each step up the chart of the elements, we add one proton to the nucleus and one electron to one of the possible shells. As we do this, we find that the electrons fill up each of these possible fuzzy orbits by pairs. Once a pair of electrons has entered a particular level, that level is sealed off to any more electrons. This is due to the Pauli exclusion principle. The reason the electrons can seemingly go into the same state in pairs is that electrons have a property called spin, which is something like the spin of a top, but as with everything else in this topsy-turvy quantum world, not quite. When we spin a top, we are free to choose any direction we wish for its axis to point. Electrons with their spin are rather different little beasts. The electron has a spin, it always has a spin, and it always has only a single speed for that spin. It can spin neither faster nor slower than this one speed. Moreover, when we set up an apparatus for measuring that spin along any arbitrarily chosen direction, we find that only two possible values can occur. The spin can point up along the instrument's axis or down along that axis. It spins with only that one possible speed, pointing only up or down along a measurement axis that we have chosen arbitrarily. Why does the electron's spin depend on the way we choose to measure it? That is another one of those strange quantum mechanical puzzles, and another clue to what reality actually is. Because the electrons have two possible spin states, two electrons, one with spin up, one with spin down, can reside in each possible level in the atom. Thus, the shells build up two by two to form larger atoms. Much later on, we will have more to say about the strange nature of electronic spin, and we will show how its odd nature is much like the very odd nature of something one might not expect to be any puzzle at all, the way light is filtered by Polaroid lenses. It is something that is very commonplace, and yet it will tear away the picture of reality we have always accepted. We will come to that much later. Right now, we must look at another principle of quantum mechanics that is a kind of first cousin to Pauli's principle. This is the principle of indistinguishability. Granted, it sounds like nomenclature for service decorations presented to soldiers on the losing side, but it accurately describes the physics of some atoms. Originally, an Indian physicist by the name of Satyendra Nath Bose advanced the idea of indistinguishability in order to understand certain things about the capacity of objects to hold heat. Einstein extended Bose's idea to establish what is now known as the Bose-Einstein statistics. Enrico Fermi and Paul Adrien Maurice Dirac extended Bose's idea and Pauli's exclusion principle to establish what is now known as Fermi-Dirac statistics. Among other things, Bose-Einstein statistics is the first step in explaining how superconductors allow an electric current to flow forever with no loss. Fermi-Dirac statistics explains why metals feel cold. Both of these ways of understanding how matter behaves depends on the idea of indistinguishability. This principle says that two identical particles, for example, two electrons or two helium atoms, have no separate identity. There is no way in which one can place a sign on one of these particles in order to distinguish it from another of the same type. One cannot put a sign on an electron that says Richard or Joe. To see what this means, let us say that John Smith and his wife Jane, who own a house in the city, decide to buy a house away from town by the sea. Now there are four ways in which John and Jane can occupy their two houses. John and Jane can both stay in their city house. They can both stay in their country house. John can stay in the city house while Jane is in the country house, or Jane can go to the city while John is off by the sea. Four ways. Now, if instead these houses were owned by Jane and her identical twin sister Jill, there would still be four arrangements, but we might be hard pressed to distinguish more than three of them. We would have trouble telling for sure whether Jane was in the city and Jill was in the country, or if Jill was in town with Jane by the city. But the reality would remain that there would be four possible arrangements anyway. Where helium atoms go and what they do when put in a bottle, and where electrons go inside a piece of metal as it conducts electricity, is a little like this business of Jane and Jill. These things can occupy different places, and as the heat is turned up on them, they switch around faster and faster. The fewer the number of places for the particles to go, the faster the temperature rises, and the sooner we notice the effects of the heat on the object. Quantum mechanics tells us just how material will behave when heated, provided we take this fact of indistinguishability into account. Because any two particles of the same type are indistinguishable to us, switching two of them around does not even exist. Matter behaves as though the fact that we cannot tell these two arrangements apart means that they cannot make such a switch. As the object is heated, it goes right past such arrangements in the rapid switching around of the particle positions in the object. Oddly, the fact that we cannot distinguish these states apart means that such things do not even exist. Why would the observability of such differences matter so much? This is another of those mysteries about quantum mechanics and about the nature of reality. It has become exceedingly clear that observability of differences matters and that it describes something vital about the nature of reality, yet it seems somehow not to fit our understanding of what this world is all about. It paints a picture of a world that is less objectively real than we usually believe it to be, but quantum mechanics describes reality in the heart of an atom and in our own macro world. If it does not make sense, then that is because we do not understand our world quite so clearly as we had thought. Why should it matter to nature whether we can distinguish two particles apart? Why should observability matter so much? The questions hint at the ultimate answer to this riddle. There is another oddity in physics that we have to discuss while we are on the subject of the idiosyncrasies of quantum mechanics, something known as quantum mechanical tunneling. Let us talk about this phenomenon of tunneling in terms of baseball, even though we all know that quantum mechanics plays its role only in the world of the atom. If a batter hits the baseball hard enough and high enough, it will go over the outfield fence some 400 feet away. and well, that's a home run. If the batter doesn't hit the ball quite so hard or quite so high, then the ball may go out and hit the fence, but it won't go out of the park and it won't be an automatic home run. But in the world of quantum mechanics, sometimes a ball that was not hit hard enough to go over the fence just rolls up to the fence and keeps on rolling. Sometimes it just keeps on rolling beyond the fence and out of the ballpark. In this quantum world, the ball does not jump over the fence, it does not knock a hole in the fence, it does not squirt between the boards or go under the fence, and it never goes inside the fence. It simply rolls up to the fence and rolls and rolls on outside the fence. It is important to understand that this now you see it, now you don't quirk of atomic reality is not a magic trick, but a part of the way nature is. This phenomenon of tunneling is so often met in quantum mechanics that it is in essence a hallmark of the quantum domain. Among the places where one commonly encounters tunneling effects is in natural radioactive decay in atoms of uranium, for example. There, the nucleus contains almost a sea of frothing particles held inside by powerful nuclear forces. None of these particles has the energy to overcome this nuclear force in order to escape, and yet occasionally an alpha particle, the nucleus of a helium atom, comes barreling out anyway. It has tunneled through the outfield fence for a home run. There is another place we will meet this business of tunneling. We will come back to this in a later chapter when we talk about the way the brain works and about what mind actually is. There we show how our brains use this phenomenology of tunneling effects in synapses to carry out the vastly complex activities that create our thoughts. We have talked about the accomplishments of quantum mechanics. We have talked about some of the puzzles with which quantum mechanics leaves us. These puzzles define something of the tasks we face in our search for reality, but we should not misunderstand what these puzzles mean. The existence of these puzzles does not diminish one whit the vast power of quantum theory to explain our world. Quantum mechanics is a firm platform for us to stand on as we search for the nature of reality. Its puzzles are but clues to discoveries that are waiting for us. Throughout so much of life, nothing really ever happens. Looking through the pages of my old diary, I see the slow pace of that southern upbringing. Days were whiled away with boring and pointless activities, or so it seemed. Looking back, knowing the beginning and knowing the end, I can see that in the meaningless details of life a larger fabric was being woven. Monday, another week, my diary lifts a corner on another long lost memory. No homeroom teacher today, American history, Miss Borders, debating class, nothing happened. Then a small adventure, going for my motor vehicle operator's license, the rite of passage. There was one problem. My parents had not exactly been apprised of my intentions. I was rushing off to carry out a mission demanded by the circumstances of the times and of youthfulness. And all the better, I had an accomplice, Marilyn. As soon as school was out, Marilyn and I took off for the medical center on 8th Avenue South, where my mother worked, and more importantly, where the family automobile waited. Absconding with the family vehicle was easy. No one stood guard, no one noticed the deed. Quickly, and with utmost skill, the vehicle was started and moved from its place of parking. Expertly, we powered the 4,000-pound four-door Pontiac Grand something or other onto the public streets and made our way, quite illegally, to 6th Avenue North, where I met Marilyn out to wait safely in the Birmingham Public Library. She was, after all, a woman. I was out to do man's business, to test my steel before the civil authorities. On 7th Avenue, I parallel parked for the first time directly across the street from the motor vehicle registration office. From my vantage point, I could see through the large storefront style windows into the interior of the driver's testing division. The men in blue uniforms looked bigger than they had when I scouted out the place. One of them looked up. He looked directly at me. Yes, I was sure of it. Panic began to set in. I thought, the line, it's too big. Mother will come out before I can finish. She'll find the car missing, stolen. She might call the police. They're all looking at me. I sped off. Marilyn was waiting. The line was too long. I blurted, I'll have to try tomorrow. We drove long, terrible miles back to 8th Avenue South. Marilyn must have sensed the mortification I felt. She saw me in this moment of ignominy, in this my farewell to arms, my manhood not won. She knew I had chickened out. I pressed harder on the gas pedal. And then we were there. As I turned into the parking lot again, terror. Someone had taken my mother's parking space. Panic raced through me. My heart pumped audibly. Hairs on my head trembled. 15 minutes to 5. My mother would be coming out at 5. It started raining. We waited. Then, as if it were a sign from God, the owners of the car emerged and vacated the space. I parallel parked for the second time in my life. Perfection. Inwardly, I smiled. I had recovered that measure of lost esteem. There was now a new feeling that I felt, a feeling of self-assuredness, of, yes, of maturity. Marilyn and I looked at each other and giggled. This next section is called Wheels Within Wheels. By 1912, physicists had finally proved the existence of the atom, which had been suspected and speculated about since the days of Democritus. By 1920, physicists had figured out the probable structure not only of the atom but also of its nucleus. The simplest atom, hydrogen, has a single particle, the proton, for its nucleus. Other atoms consist of a nucleus made up of a collection of protons that are equal in number to the electrons in orbits around the nucleus, so that the negative electric charge of these electrons exactly balances the positive charge of the proton. But except for hydrogen, this picture leaves about half the mass of the atom unaccounted for. Physicists reasoned there had to be another kind of particle, a neutral particle in the nucleus along with the protons. Rutherford, who had proved the atom consists of a massive, positively charged core surrounded by electrons, searched in vain for this neutral particle. Finally, in 1932, James Chadwick, who had worked with Rutherford in the Cavendish Laboratory in Cambridge, England, proved the existence of these neutrons. He was able to show that the sought-for neutrons had been produced 2 years earlier in a series of puzzling experiments conducted by both at the Kaiser Wilhelm Institute in Berlin. The new particles had just the right mass to explain the structure of the atomic nucleus. The results of this was what finally seemed to be a complete picture of matter as made up entirely of three elementary particles, protons, neutrons, and electrons, from which all ponderable objects are formed. These three particles made possible an explanation of all the 92 elements that occurred naturally in nature, but there was still a missing ingredient, what holds the nucleus itself together. There must be another force that binds all the protons and neutrons into that very tight nuclear ball. Otherwise, what is to prevent all those nuclei with all their mutually repelling protons from flying apart in an instant? There must be a nuclear force. The search was then on to find the secret of the strong force within the atomic nucleus. This new kind of force would have to be totally different from either the gravitational or electromagnetic force. This new force would also have to be far stronger than either of these other well understood forces, and yet, unlike these other forces, the nuclear force would be something totally undetectable outside the nucleus. In other words, it has an incredibly short range. In many ways, the strong force is more like a glue that sticks things together than a force. It acts powerfully up close but falls off exponentially as the particles are separated. The force falls off so fast that it is not possible to do conventional experiments to find it. We cannot very well hold two neutrons a trillionth of an inch apart and measure the force between them. Instead, perhaps the thing to do is look for a radiation caused by this force acting between the two particles as they collide. In other words, look for the photons of this strong nuclear force. What was needed was some idea as to what to look for. This is where Hideki Yukawa entered with an idea that was to entirely change the way physicists conceive of the basic forces of nature. Yukawa, while working toward his doctorate at Osaka University in 1935, proposed that the strong nuclear force was carried by a particle having a ponderable mass, that is, that the particle produced by disturbing the nuclear force field would be more like ordinary matter, having a rest mass as opposed to the photon that only has a mass that is equivalent to the energy carried by the electromagnetic radiation. For the photon, there is no such thing as a rest mass. The photon always travels, obviously, with the speed of light. But Yukawa's carrier of force would have a rest mass and could travel at any speed. Any speed, that is, that Einstein's relativity would permit. Yukawa was able to say just how much mass this new particle would have to have if it were to explain the strong force within the atomic nucleus. The mass would have to be intermediate between that of the proton or neutron and the mass of the electron, something like 300 times the mass of the electron. For this reason, the proposed particle was called a mesotron, later simplified to meson. 2 years later, particles fitting this description appeared as faint tracks in cloud chamber experiments. It looked like things were complete. At last, the whole universe seemed to be explained in terms of these few particles and these few forces. Everything from galaxies to station wagons, uranium to barking dogs, everything. The cosmic onion had been peeled away to show all the pieces that made up the basic building blocks of reality. All the answers. The proton, the neutron, and the electron, together with Newton's universal gravitation, Maxwell's electromagnetic force field, and Yukawa's strong nuclear force, it looked pretty good. But the looks were deceiving. Before the ink had dried, everything fell apart. The Yukawa meson found in the cosmic ray tracks in the cloud chamber experiments turned out to be the wrong meson. It simply did not interact with matter strongly enough to provide a glue that would hold a nucleus together. The search was on to find the right particle to make Yukawa's picture of the strong force work. The right particle, or rather the right particles, were found, but in the process, the search turned up a whole series of new particles and strange discoveries about these elementary particles that made them appear less and less the elementary building blocks originally envisioned. While all this was going on, the mathematical machinery that physicists use to understand how these particles and fields of force interact also developed rapidly, giving us more certainty and accuracy about the way we describe nature. P.A.M. Dirac, who we last met extending Bose's indistinguishability principle, had Pauli's exclusion principle, succeeded in fusing Schrödinger's wave mechanics and Einstein's special theory of relativity into a single powerful tool that has stood to this day as the most precise achievement in all physics. To show just how successful this theory has proved to be, let me quote from Richard Feynman's book, QED, The Strange Theory of Light and Matter. And this is the quote from that book. Just to give you an idea of how the theory has been put through the ringer, I'll give you some recent numbers. Experiments have Dirac's number at 1.001159652221 with an uncertainty of about 4 in the last digit. The theory puts it at 1.0011596246 with an uncertainty of about 5 times as much. To give you a feeling for the accuracy of these numbers, it comes out something like this. If you were to measure the distance from Los Angeles to New York to this accuracy, it would be exact to the thickness of a human hair. That's how delicately quantum electrodynamics has, in the past 50 years, been checked. One of the significant achievements involving Dirac's equation was his use of it to predict a positively charged electron. Dirac came to this conclusion in 1931. A year later, Carl Anderson in the United States found this positive electron, or positron, as it is now called. Dirac's equation gives us further insight into the mysteries of the wave-particle duality. Dirac's quantum electrodynamics, or QED, is a quantum theory of force fields. Just as in the wave-particle duality, every particle also behaves like a wave. In the quantum theory of fields, every force field also has its own kind of particle that carries that force. The electromagnetic field that produces a repulsive force between two electrons, or that causes two magnets to repel each other when like poles are brought together, is caused by photons, virtual photons emitted and absorbed between the two objects. It is somewhat like two swimmers tossing a beach ball back and forth between them. The repeated impulses caused by throwing and catching the ball will slowly cause the two to drift apart as if repelled by some beach ball field. If instead of throwing this beach ball through air, the swimmers were to try to throw the ball between them underwater, the only way one can do this is by rapidly paddling the water out of the ball's way. They would be drawn toward each other just as the attractive electric force between a proton and electron pulls the two together in forming an atom of hydrogen. The photons emitted and absorbed by the electrons can, of course, be real photons, just as we have been picturing these pieces of electromagnetic energy. But even when light is not being radiated in the conventional sense, the electric force between two electrons is there and is caused by the virtual photons being exchanged back and forth. These photons are called virtual because even though they exist to produce the force, there is not sufficient energy in the system of particles for them to exist as free particles, as photons. This change in our perspective about what a force field is makes it all the more difficult to talk about elementary particles. Particles are continually being created and annihilated in order for the fields to exist. The electron itself must be thought of as surrounded by a cloud of photons that in their turn are continually created and destroying electron-positron pairs. As the electron moves through the vacuum of space, this cloud of photons, electrons, and positrons is forming, being polarized by the passage of the electron, and then disappearing. All of these particles being created and annihilated are the cycles and epicycles of quantum vibrations in these fields. The situation is even more complicated than that. The meson that was originally thought to be the particle of Yukawa force turns out to be a kind of heavy electron. The particle has nothing to do with the force that binds the nucleus together. It is just a fat electron. It has been renamed simply the muon. It can decay into an electron and two neutral particles called neutrinos. These particles are also a part of the cloud of virtual particles surrounding the electron. Protons and neutrons, the particles that make up the nuclei of atoms, also exist as clouds of particles, but their structure is more complicated and involves a cluster of new particles that we will address a bit later. In addition to all these particles, there are the real mesons. These particles turn out to be the particles predicted by Yukawa that produced a strong force within the nucleus. But the story turned out to be more complicated than had been envisioned. Rather than there being one meson that would have explained the strong nuclear force inside the nucleus, it turns out that there were many mesons. The search turned up particles called pi mesons, or pion. The search found a positive pi, a negative pi, and a pi with no charge at all. Physicists discovered the rho meson. They also found the K mesons. They found the eta, the phi, and the omega. They found the epsilon, the upsilon, the z, and the psi. There were so many that they switched from Greek and named them by Roman letters and used asterisks. S asterisk and K asterisk and primes like F and subscripts 1, 2, and 3. They found B, F, and G. They found M, Q, S, U. They found mesons that were strange and mesons they called charmed. They found these particles and they found their antiparticles. All these to decorate the meson particle charts, and each sporting various characteristics to distinguish each in this long list of mesons. Inside the nucleus, all these mesons seethe in a maelstrom of creation and annihilation, cycles and epicycles. In addition to this long list of meson particles, we must add the list of the heavier particles which are more or less similar to the proton and neutron originally envisioned as the sole inhabitants of the atom's nucleus. These particles are known collectively as baryons and include as species lambda, sigma, z, omega, and delta particles. The lambda particles alone come with masses of 2180, 2605, 2750, 2975, 3130, 3270, 3305, 3520, 3550, 3580, 3640, 3935, 3955, 4110, 4130, 4550, 4600, and 5060 as measured in terms of the electron mass, and the list of sigma particles is even longer. Each comes in an assortment of types, charges, and antiparticle forms. The list of subatomic particles, once thought to be the elementary particles of the universe, has now grown to include more than 400. The cosmic onion has been peeled back to reveal more onion. But if the perplexity revealed by unfolding the superfluidity of particles has seemed bewildering, steady and sometimes brilliant progress has been made in divining the secrets deep within nature's hidden machinery. Physicists using machines that are miles across and cost billions of dollars have probed still deeper into the interior of even these subatomic particles to find the pieces of which they are made. This next section is called Quark, Quark, Quark. Looking deeper into the structure of matter, physicists have found a new set of particles that like to cluster into groups of twos and threes. These are the particles that are called quarks. This fanciful name comes from a line in James Joyce's Finnegan's Wake, 3 quarks for a muster mark, which Murray Gell-Mann quoted when he first presented the theory of their existence. To see how these quarks simplify our understanding of matter, let us list in groups of all the particles that we have talked about. There are 4 groups to keep in mind at this point. This number will change as soon as we see how 2 of these groups can be explained in terms of quarks, but for now there are 4. 1 quanta, 2 leptons, 3 mesons, and 4 baryons. The quanta are the particles that explain the forces like electromagnetism and gravitation. We have already talked at some length about electromagnetism and gravitation. Electromagnetism involves the photons, the particles of light. Physicists believe gravitation is caused by particles called gravitons. We will talk later about the quanta associated with the other 2 kinds of forces, the stronger nuclear force and the weak force. The second group of particles is called the leptons. The name comes from the Greek for small, in particular, a small coin, presently equal to 1/100th of a drachma, and refers to the fact that these particles are very light. The ones we have already mentioned are the electron and the muon. There also exists the neutrino, a neutral particle that is emitted along with the electron in the radioactive decay of some atoms. The muon acts in every way as though it were just a heavy electron. It even has its own neutrino associated with it, called simply the muon neutrino. A third pair of these particles are known as the tau particle and its tau neutrino. Within the limits of the present experimental evidence, neutrinos have no mass, or if they have any mass, it must be extremely small. The third group consists of the meson particles, which we discussed as perhaps playing a role in keeping the nucleus together. The operative word here is perhaps. The way things actually work turned out to be somewhat different and somewhat simpler than Yukawa had thought. The baryons, which constitute the fourth group, are rather heavy particles that include protons and neutrons and interact with other particles as though they were protons or neutrons. These last 2 groups of particles, the mesons and baryons, are so numerous that they overstuff the atomic cornucopia. Furthermore, these last 2 groups can now be understood in terms of more fundamental constituents, revealing a basic simplicity in the structure of matter. It turns out that all the mesons consist of a pair of the particles called quarks. Baryons, including protons and neutrons, consist of 3 quarks. No free quark has been found. So far, quarks have always been found in groups of at least 2. Because of this, the types of quarks must be inferred from the various possible interactions that can occur among the collections of quarks, that is, among the various mesons and baryons. It is now fairly well established that there are 6 kinds of quarks and no more. It is believed that all 6 kinds of these quarks have been found in particle collision experiments. The quarks are named up, down, strange, charm, bottom, and top. Originally, the names beauty and truth were given to the last 2. This led to too many lovely quips, such as, "There is no truth to be found in quarks." The uses to which the names beauty and bottom could be put, they had both continued to be used, might have resulted in some ultimate decline in the productivity of theoretical physicists had not steps been taken in time. As for me, I still prefer the names beauty and truth, A particle containing a single quark of a given type, such as beauty, is said to show naked beauty. Better a naked beauty than a naked bottom, if one is to use absolutely preposterous names that have nothing to do with the internal structure or dynamics of the particles. It would be nice if one could at least use a modicum of literary taste. Lately, physicists have taken to using simply the letters U, D, S, C, B, and T. Perhaps that is just as well. There was never anything particularly worthy of a literary gesture here anyway. At least the designations U, D, S, C, B, and T save space and time. These six kinds of quarks are thought of as being distinct particles, despite the fact that they never appear alone. These six types are also referred to as being the different flavors of quarks. One can therefore have a quark with the flavor property of up, or even speak of a quark as having a strange flavor. I am not making this up. All the quarks carry an electric charge. Strange, bottom, and down all carry a negative charge that is 1/3 of that on the electron. Quarks with the flavors charm, top, and up carry a positive charge that is 2/3 as large as that on an electron. A proton consists of two up quarks and one down quark. That means its total electric charge is plus 2/3 plus 2/3 minus 1/3 equals plus 1. A charge equal to that on an electron, but of opposite sign. A neutron consists of two down-flavored quarks and one up quark. The electric charge is therefore negative 1/3. Negative 1/3 plus 2/3 equals 0. The antiproton consists of two anti-up flavored antiquarks and one anti-down antiquark for a total charge of negative 2/3. Negative 2/3 plus 1/3 equals minus 1. That is, it is a proton with a charge that is negative, just like that of an electron. All baryons turn out to consist of three quarks. All mesons can be explained as consisting of quark-antiquark pairs. For example, a down quark and an anti-down quark give a neutral pion, one of Yukawa's mesons, and the psi meson consists of a charm-flavored quark and an anti-charmed antiquark. The nuclei of atoms are held together by the exchange of various mesons, which really involves the exchange of quark-antiquark pairs among the protons and neutrons in the nucleus. The process, however, is rather more complex than this, as we shall see later. Now let us look at what holds quarks together in the pairs forming mesons and triplets forming baryons. The force is called the strong force. The particles holding the quarks together are called gluons. There are 8 different gluons. The theory behind this force is called chromodynamics. The reason for the colorful name is that there seem to be 3 kinds of charges necessary to explain the strong force. Because there are 3 basic colors, these charges have been given colors for their names, red, blue, and green. Thus we find that the strong force that at first was thought to be due to Yukawa's mesons is actually caused by the gluons. The mesons are still there, but now we see that there are themselves pairs of quarks held together by gluon forces. They are, in turn, constantly being exchanged among the baryon particles that make up the nucleus. Now let us back up just a bit. The force of gravitation pulls on all objects. We can think of gravitation as a force that has only one kind of charge, a positive charge called mass, carried by all pieces of matter. Electromagnetic forces, however, act only on particles that carry an electric charge. Furthermore, there are two kinds of electric charges, positive and negative. In chromodynamics, the theory that explains how the strong forces act, there are three kinds of charges, or colors, as they are called: red, blue, and green. Like the three primary phosphors that produce colors on a television screen. But nature is clever and has not only stepped up to three kinds of charges, but has also embedded something like positive and negative electric charges here, for there also exist positive and negative colors. The negative colors are called anti-red, anti-blue, and anti-green. The gravitational force is carried by gravitons, the electromagnetic force by photons, and chromodynamics tells us that the particles that carry the strong force are gluons. Gravitons act on particles that have mass. Photons act on particles that have electric charge. Gluons act on quarks that carry color. There are red up quarks, blue up quarks, and green up quarks, which come in the anticolors yellow, cyan, and magenta. The colors my former physicist colleagues call anti-blue, anti-red, and anti-green. There are red down quarks, blue down quarks, magenta down quarks, red bottom beauties, magenta bottoms, and blue tops, forsooth. All the flavors come in all the colors. True or false, chromodynamics is definitely garish. Now there is a rule that governs how these colored quarks of the various flavors can combine to form objects we can see, that is, objects we can detect in our experiments. The objects made of quarks are all colored neutral. Thus, objects, mesons, made of two quarks must contain a quark of any color together with an antiquark that carries the opposite color. Therefore, there can be mesons that are made out of red up quarks together with a cyan up quark, a blue down and a yellow up quark, a green bottom pair with a strange magenta quark, and so on. The baryons must also have neutral color. The three quarks that make up a proton, for example, must carry one each of the basic colors red, blue, and green that, when mixed together, give us white. Every baryon must have one each of these colors, or one each of the anticolors yellow, cyan, and magenta that, when mixed together, also give a neutral color. It is a flower garden. Hidden within the fabric of reality lies this imaginary herb and flower garden filled with flavors and colors. But there is more. Inside these flower gardens are the gluons that hold the various quarks together to form mesons and baryons. The gluons, like bees carrying pollen, exchange colors between quarks. Each gluon can carry one color and one anticolor of any kind. A gluon can, for example, be red and magenta, anti-green, inside a proton containing, say, a red up quark, a blue up quark, and a green down quark. A red magenta gluon forms out of the red up quark. The red color of the up quark passes into the gluon, and magenta, anti-green, forms as the gluon leaves green color behind in this up quark. Now the gluon travels to the green down quark, where the magenta neutralizes its green color, which permits the red to be deposited to form a red down quark. It is certainly more complicated than the photon exchange that keeps an electron circling the charged nucleus of an atom. Gluons, like bees, can also interact with one another. This interaction is simple. For example, a red magenta anti green gluon interacting with a blue cyan anti green gluon turns into a single blue magenta gluon. The anti red cyan on one gluon joins with the red on the other gluon to cancel out, leaving just one gluon carrying a TV color blue and a Xerox color magenta. With chromodynamics, we can explain just about everything that mesons and baryons do. However, there is still another kind of interaction that can take place, and there is yet another kind of force. The weak force has its own set of particles that carry the force and a set of effects that the force can inflict on the particles subject to it. This weak force ties together, so to speak, the leptons and the quarks. The weak force is carried by a trinity of very heavy particles, the W positive, W negative, and Z particles. The W positive particles carries a positive electric charge, while the W negative particles carries a negative electric charge, like the electron, and the Z carries no charge. This trinity of particles has the ability to change the flavors of quarks. For example, they can change a down quark into an up quark. Our inventory then includes 1. The four forces: gravitation, electromagnetism, the strong nuclear force, and the weak nuclear force; 2. The quarks that form the mesons and baryons; and 3. The leptons, electrons, muons, and tau particles, along with their neutrinos. The four forces involve the graviton, the photon, 8 gluons, and 3 particles that carry the weak force, that is 13 particles. Then there are the leptons, electrons, electron neutrinos, and their antiparticles, the positron and electron antineutron, the muon, which looks in every way just like an electron, except that it is heavier. It's muon neutrino and their 2 antiparticles, and the tau, which is just a fat muon, together with its neutrino and their antiparticles, that is 12 leptons. Finally, we have the set of 6 quarks, which come in 6 flavors and 3 TV colors, together with an entire set of antiquarks having Xerox colors and opposite electric charges. This makes a total of 36 kind of quarks. Thus, we have 36 quarks, 12 leptons, and 13 particles involved with the four forces. Altogether, that makes 61 kinds of particles. That is the standard model. In addition to these, there is one more particle called a Higgs boson, a particle expected to be like the quanta, i.e., the chunks of energy, postulated to give the W positive, W negative, and neutral Z particles their heavy masses. To say the least, as Chris Quigg put it in Scientific America, by the criterion of simplicity, the standard model does not seem to represent progress over the ancient view of matter as made up of earth, air, fire, and water interacting through love and strife. The standard model does enormously simplify the profusion of mesons and hyperons. Still, it seems that all these particles are just some Neo-Ptolemaic theory of epicycles miraculously resurrected from the dusty pages of Roman history. Despite the magnificent science that all this represents, it sometimes seems that the true nature of reality has eluded us. There are so many particles with so many properties, colors, charges, colors, flavors, spins, masses, that it seems as though the answers have simply been pieced together. Maybe the theory fits the facts, but there are enough knobs and dials and spare parts in the theory that it can easily be changed to fit most any set of facts. The problem of the predicted decay of protons is a case in point. This prediction arose from efforts to reduce further the complexity of the basic theory. A unified theory would let us understand quarks as made out of leptons. After all, the Standard Model details how neutrons decay by showing that a down quark can decay to produce an electron and an electron antineutrino. Perhaps quarks are made out of such things. This grand unified theory, GUT, reduces the total number of particles, but it also requires a few new ones. The theory predicts that protons should decay somewhat the way the neutron decays into a proton and an electron with the emission of a neutrino. In this new theory, the up quarks in the proton can decay into photons. Thus, the protons in ordinary matter should decay away. At first, it looks like the theory predicted that all the protons in all the nuclei of all the atoms should have disappeared, but then the theory was fixed. In the fixed up theory, protons would still decay, but at a very slow rate. The experiments to test this proved to be difficult and very expensive, and they failed to find any such decay. The maximum possible half-life for the proton would have to be more than 1.7 times 10 to the 32nd power in years, but the theory was fixed up to agree with even this lower rate of proton decay. And this points out one of the weaknesses of a theory that embraces such a large number of basic particles. Surely these particles have something to do with reality, but the ease with which large numbers of alternative theories can be created detracts from the significance of all these theories. We are left feeling that these theories may have no more to do with the real structure of ultimate reality, whatever that may be, than Ptolemy's epicycles, which you will recall did explain the planet's motions. This next section is small, but it is called Deeper Structures. It's only a single paragraph. Physicists have begun to look even deeper into the structure of matter, looking for ways to reduce the total number of particles necessary to explain everything, and ways to clear up some of the puzzling things about quarks and leptons. Why, for example, has nature given us a chubby electron, the muon, that is 207 times the mass of the electron, and an out and out obese tau particle in every way just like the electron, except that it weighs in at about 3,480 electron masses? Why does each of these have its own similarly mysterious neutrino? The quarks also seem to come in three sets of particles. Such groupings suggest that these particles may have some internal structure. Perhaps if we looked for things even smaller, we will find the secret of the universe. Perhaps the universe is made of strings of vibrating space-time. End of that section. And this next section is called Strings in the Fabric, ? All this buttoning and unbuttoning. This enigmatic phrase from an 18th century suicide note somehow reminds me of the frantic search for elementary particles. And that phrase was all this buttoning and unbuttoning. Finding so many possible levels of compositeness as they look deeper and deeper into matter, physicists surely should have begun to ask, where will it finally end? Does it go on forever? If we search at higher and higher energies to find smaller and smaller bits of matter, will we ever find the smallest pieces? Recently, physicists have begun looking at what they call the theory of everything, or TOE, to unify all the fundamental forces, identify all the particles, explain their masses, and account for the rules governing the composite structures. The idea is to attempt to explain all the forces of nature the way Einstein explained the force of gravitation as being due to a distortion in spacetime caused by the presence of matter. In superstring theory, this kind of space warp force takes place in a 10-dimensional spacetime, 9 space-like dimensions and the usual time dimension. Particles are considered to be string-like loops in this 10-dimensional spacetime, strings that can vibrate much like the pictures we imagined for the de Broglie waves of electrons in orbit around the proton. The difference is that these strings are able to distort space into exceedingly tight loops, so tight that 6 of the dimensions curl up so that we can see nothing of them but the effects they have on these string-like particles. But more than this, the strings themselves are nothing but vibrating distortions of space. In this theory of everything, the particle is just a space wave, an almost infinitely tiny vibrating knot in space, just 10 to the negative 33 powered centimeters small. But what is space and what is time? We have already seen that space and time are both relative concepts. They are not some absolute substance from which we could roll up pieces of matter. It seems almost as if in our search to understand what matter really is and what reality is all about, we reach into the very seeds of creation to find only a void. I do not want you to misunderstand me here, however. We have probed to incomprehensibly small distances and unimaginably brief instants of time. There is great achievement in all this. Science has discovered much. The engineering is wonderful, epicycles and all. And yet, as we look at this vast, elaborate structure built of layer upon layer of complex constituents, can we help but be reminded of the land of Oz? Have we found the Emerald City? Is this what we were searching for? Is this the ultimate fabric of reality? Is this all there is? A long way I have come, a long way now, far from that open grassy ridge west of Auburn. Those distant hills lie in the past, but the questions have remained. There was something more to her, so far back in my past that is gone from all the atoms that once breathed the same warm air that I breathed, and I do not find any of her here in the quarks and the leptons or in any of the superstrings of spacetime. I remember a cocked head, a laughing voice, and a glance decades away. Somewhere in our search for reality, we have passed something by, something important that we no longer find amid the bits and pieces of disassembled matter, something vital that we cannot build out of these parts. There is surely something else, some piece of divinity in us, something that was before the elements and owes no homage to the sun. End of chapter.